Picture this, a rover on Mars, but not the kind you're used to seeing. Instead of wheels, it has 6 slender, articulated legs, moving with the quiet confidence of an insect, stepping nimbly over jagged rocks and sinking sand, climbing slopes that would trap a conventional rover in an instant. This isn't a scene from a distant sci-fi fantasy. It's the thrilling and tangible future of robotic space exploration, and it's being shaped not in a sterile lab alone, but by looking closely at some of nature's oldest and most ingenious engineers, insects. For decades, wheeled rovers have been our eyes and hands on other worlds, heroic machines that have rewritten textbooks and expanded our understanding of the cosmos. But as breathtaking as their journeys have been, they've also revealed real limitations. Wheels, for all their simplicity on paved roads, struggle in environments that are unpredictable, soft, or brutally uneven. We've watched rovers get stuck, lose traction, or simply be unable to reach the most tantalizing, scientifically rich locations: the steep crater walls, the hidden cave networks, the unstable slopes that might hold clues to life itself. It's become clear that if we truly want to deepen our reach into the universe, we need a new approach to mobility, one that's as adaptable, resilient, and resourceful as life on Earth has proven to be over millions of years. That's where the incredible world of insects comes in. These small but mighty creatures have mastered movement across every kind of terrain our planet can throw at them, from shifting deserts to dense rainforests, from vertical cliffs to unstable rubble. They do it with an elegance and efficiency that our best engineering is only beginning to understand. In this video, we're going to explore why the next generation of space rovers may leave the wheel behind and step into the future on legs inspired by ants, beetles, and cockroaches. We'll dive into the biomechanics that make insects so unstoppable, the evolutionary advantages that could revolutionize extraterrestrial robotics, and how these designs might soon help us overcome obstacles we once thought were impossible. This is a story about looking down at the ground beneath our feet to learn how to traverse worlds far above, a journey where biology and technology merge to help us go farther, see more, and dream bigger than ever before. Think about the monumental success of rovers like Curiosity and Perseverance. These incredible machines have trundled across the Martian surface, beaming back breathtaking images and groundbreaking data that have fundamentally changed our understanding of the Red Planet. Their contributions are nothing short of legendary, but even legends have their weaknesses, and for these wheeled explorers, the very landscapes they are designed to conquer often present their greatest challenges. The fundamental issue lies in the wheel itself, a technology that works beautifully on prepared, predictable surfaces here on Earth, but can become a critical liability in the utterly alien and unforgiving environments of other worlds. One of the most persistent adversaries for a wheeled rover is terrain covered in loose, sandy material known as regolith. Picture a dune of fine, dust-like soil that offers no firm traction. Wheels are designed to roll, but in these conditions they can easily dig themselves in, spinning futilely and sinking deeper with every attempt to break free. This isn't just a theoretical problem, it's a mission-ending reality. The heart-wrenching example is the Mars exploration rover Spirit. After 6 years of prolific work that far exceeded its original 90-day mission, Spirit's journey came to an abrupt halt in 2009 when its wheels broke through a crust of surface soil and became permanently embedded in soft sand beneath. Despite exhaustive efforts from the team on Earth, Spirit was unable to free itself and transition from a mobile explorer to a stationary science platform. Its mission of mobility ultimately cut short by terrain it simply wasn't built to handle. Beyond soft sand, sharp volcanic rocks litter the Martian ground like natural landmines, posing a constant threat of punctures and damage to the wheels themselves. We've seen the visible wear and tear on Curiosity's wheels, with holes and tears appearing from repeatedly driving over these jagged obstacles. While engineers have designed later models with tougher wheels, it remains a persistent vulnerability that mission planners must constantly navigate around, often forcing rovers to take long, tedious detours to avoid the roughest patches. Then there's the challenge of steep inclines. Wheels rely on friction to climb, and on a world with different gravity and no paved roads, even a relatively gentle slope can become an insurmountable barrier. A slope that might be a minor inconvenience for a hiker can be an impossible cliff for a wheeled vehicle, severely limiting the scientific targets a rover can even attempt to reach. This combination of hazards, the sinkholes of fine regolith, the daggers of ancient rock, and the intimidating slopes, creates a landscape of constant risk. Every drive is a calculated gamble, and getting stuck isn't just a minor setback, it's a potential mission finale. This inherent limitation directly impacts the scientific return of these multi-billion-dollar endeavors. The most geologically interesting sites, like the steep walls of craters where layers of history are exposed or the intriguing mouths of caves that could shelter signs of life, are often deemed too risky to approach. We are, in effect, leaving some of the most compelling stories on the table because our current tools cannot safely turn the page. As we set our sights on more diverse and extreme worlds, the icy, fractured terrain of Jupiter's moon Europa, the rugged, asteroid surfaces of the belt, or the deep canyons of Mars, the limitations of the wheel become even more pronounced. It's clear that to truly embrace the future of exploration, we need a new paradigm of movement, one born not from our highways, but from nature's most versatile and ancient travelers. So if wheels, for all their historical success, are fundamentally limited by the unpredictability of alien landscapes, where do we turn for inspiration? The answer has been crawling under our feet and flying past our heads for hundreds of millions of years. To revolutionize how we move across other worlds, engineers are looking to the ultimate masters of terrain, insects. This isn't about building a mechanical bug for the sake of novelty. It's about recognizing that evolution is the most rigorous and ingenious engineering lab in existence. Over 400 million years, insects have been relentlessly field-tested and refined in every environment Earth has to offer. They have passed the ultimate stress test of survival, and their designs come pre-optimized for challenges we are only just beginning to face on other planets. Consider the sheer diversity of landscapes an insect conquers without a second thought. A single ant colony might operate across hard-packed earth, loose sand, slick leaves, and vertical tree bark, all in one afternoon. This requires an incredible ability to adapt on the fly, something a rigid wheeled system simply cannot do. An insect's leg is a multi-purpose marvel of biomechanics. It's a shock absorber, a climbing hook, a sensor platform, and a powerful lever all in one. Each step is a complex calculation of pressure, angle, and grip, allowing them to maintain stability on surfaces that would be comically impossible for a wheel. They don't just drive over the terrain, they interact with it, using their multiple points of contact to distribute weight and find secure footing. The raw performance metrics of these tiny creatures are enough to make any engineer's jaw drop. An ant can carry objects 50 times its own body weight while scaling a vertical glass wall, a feat of strength and adhesion that defies our everyday intuition. A cockroach can sprint at speeds equivalent to a human running over 200 miles per hour, all while processing sensory information to navigate chaotic rubble piles in a fraction of a second. A dung beetle can traverse scorching desert sands, using its spindly legs to minimize contact with the hot ground while simultaneously navigating by the light of the Milky Way. These aren't just fun facts, they are proof of concept demonstrations that evolution has already solved problems we are spending millions of dollars to address. This evolutionary mastery provides a priceless blueprint. Instead of starting from a blank sheet of paper, roboticists can reverse engineer these proven biological designs. They study the precise joint mechanisms that allow a beetle to right itself after being flipped over. They analyze the microscopic hairs on a spider's foot that allow it to cling to surfaces using atomic-level van der Waals forces. They decode the neural pathways that enable a centipede to coordinate dozens of legs in perfect, unstoppable harmony. This field, known as biomimicry, is about humility, acknowledging that nature has already developed brilliant solutions and that our job is to learn, adapt, and apply them to new challenges. The potential for space exploration is staggering. By borrowing these ancient, time-tested strategies, we can design rovers that are inherently more resilient and efficient. A six-legged rover inspired by an ant wouldn't just avoid getting stuck in Martian sand. It could walk across it by using its legs to fluidly distribute its weight, much like a desert insect does. A robot with adhesive feet, inspired by a beetle, could anchor itself to the surface of an asteroid with negligible gravity, allowing it to conduct experiments without drifting away into the void. This isn't merely about adding legs to a rover. It's about integrating an entirely new philosophy of movement, one based on interaction and adaptation rather than simple, brute force rolling. This profound shift in design thinking opens the door to exploring the most scientifically compelling and previously unreachable places in our solar system. So what does this insect-inspired approach actually look like in action? The advantages of legged locomotion are profound and multifaceted, fundamentally changing the relationship between a robot and its environment. Instead of being a passive passenger rolling across the top of the terrain, a legged rover becomes an active participant, engaging with the ground in a dynamic and intelligent dance. Its primary superpower is the ability to step over obstacles rather than being forced to go through them or around them. A sharp rock that could puncture a wheel is merely a minor bump to step across for a robot with articulated legs. A deep crack in the ground becomes a simple gap to stride over, not a potential trap. This alone dramatically reduces mission risk and opens up direct paths to scientific targets that were previously considered no-go zones. The magic lies in the dynamic stability that multiple legs provide. Imagine a six-legged rover moving across a field of boulders. At any given moment, it can keep at least 3 legs firmly planted on stable ground, forming a stable tripod base while the other 3 legs are in motion, carefully probing for the next secure foothold. This constant shifting balance is something wheels can never achieve. A wheeled vehicle is either fully on the ground or it's not, with no in-between. This legged system can also instantly adapt its gait, the pattern of its steps, to match the challenge right in front of it. On flat, hard ground, it might use an efficient, wave-like walking gait to conserve energy. But when it encounters a steep, soft slope, it can switch to a more powerful, deliberate climbing gait, digging its feet in for maximum traction, much like a mountain climber kicking steps into snow. This real-time adaptability is a complete game-changer for navigating the utterly unpredictable landscapes of other worlds. Beyond pure mobility, legs offer a fantastic bonus: functional versatility. Each leg is essentially a powerful, precise robotic arm. This means the rover doesn't need a separate, dedicated robotic arm for sample collection, which saves weight, power, and complexity. The same limb that just carried the rover up a hill can gently reach down, use a tool on its foot to scrape at a rock, pick up a selected sample, and then bring it up to the main body for analysis. It could use one leg to steady itself against a large boulder, while using another to place a seismic sensor directly onto the ground. This multifunctional design transforms the rover from a simple mobile platform into a dexterous field geologist, capable of interacting with its environment in sophisticated ways that we once only dreamed of. This combination of superior mobility, inherent stability, and versatile functionality makes legged designs the ideal candidate for the next frontier of exploration. On the Moon, they could climb down into the permanently shadowed craters at the poles to investigate water ice deposits. On an asteroid with almost no gravity, legs could be used to gently latch onto the surface, preventing the rover from bouncing off into space with every operation. On Mars, they could finally grant us access to the vertical cliff faces of the Valles Marineris Canyon system, where billions of years of geological history are exposed in layers, just waiting to be read. By embracing the principles of legged locomotion, we are not just building a better rover, we are building a more capable partner in discovery, one that can go wherever the science leads us. But this incredible mobility would mean nothing if the rover's batteries died after just a few hours of operation. In the unforgiving vacuum of space, energy isn't just a utility. It's the single most precious commodity on board, and every single joule must be spent with the utmost care. This is where insect-inspired design shifts from being merely innovative to being truly revolutionary, because these creatures are not just masters of movement, they are the ultimate grandmasters of energy conservation. After hundreds of millions of years of evolution, they have perfected the art of doing more with less, and their strategies for extreme efficiency are exactly what our interstellar explorers need. Consider the humble ant on its long march back to the colony. It isn't burning energy with every muscle fiber in a constant, straining effort. Instead, it utilizes a concept known as passive dynamics. Its exoskeleton and the very structure of its legs are designed to work with physics, not against it. The insect's gait creates a natural pendulum-like motion, allowing momentum to carry its limbs forward with minimal active muscle input. It also employs elastic energy storage, where the flexible parts of its exoskeleton act like tiny springs. When a leg presses down, it stores energy, and then it releases that energy to help propel the leg back up for the next step. This recycling of energy dramatically reduces the overall metabolic cost of movement. For a space rover, this biological principle translates into a radically different engineering approach. Instead of power-hungry motors driving every single joint movement with brute force, a legged rover could be built with compliant materials and clever mechanics that allow its limbs to swing and bounce with a natural, energy-efficient rhythm, significantly cutting down on the power required for every single meter traveled. The implications for mission endurance are staggering. Current rovers like Perseverance rely on a multi-mission radioisotope thermoelectric generator, or MMRTG, which converts the heat from the decay of plutonium into electricity. This provides a steady, reliable trickle of power for years, but it is a finite resource with a predictable decline. Solar power, another common option, is entirely dependent on the availability of sunlight, which can be scarce on dusty worlds like Mars or non-existent during long lunar nights. An insect-inspired rover that sips power rather than guzzles it could stretch these limited energy budgets in extraordinary ways. It could travel farther on a single charge, conduct more experiments, and ultimately remain operational for years longer than initially planned. This extended lifespan doesn't just mean more data. It transforms the entire mission profile, allowing for riskier, more ambitious journeys to distant locations that were previously considered too energy-intensive to even attempt. Furthermore, this efficiency leads to a cascade of beneficial design choices. Lower power requirements could allow for smaller, lighter batteries or a smaller radioisotope power source, which in turn reduces the overall mass of the rover. A lighter rover is easier and cheaper to launch from Earth, and it places less stress on its own limbs and joints during operation, further enhancing its longevity. It creates a virtuous cycle of efficiency where every watt saved contributes to a stronger, leaner, and more resilient machine. This isn't just an incremental improvement. It's a fundamental rethinking of how a rover interacts with its most valuable resource, paving the way for missions that are not only more capable but also more sustainable in the long-term exploration of our solar system. This inherent stability offered by multiple legs is about more than just not falling over. It's about creating a rock-solid, mobile laboratory that can operate with confidence in the most treacherous places imaginable. Think of it as the difference between trying to balance on a ladder with 2 feet versus having the unshakable foundation of a 6-legged scaffolding system. Each leg acts as a strategic outpost, distributing the rover's weight so effectively across the ground that the pressure on any single point is dramatically reduced. On a world like Mars, where the surface can be a deceptive mix of crusty dirt hiding powder-fine sand beneath, this is the difference between gliding across the top and sinking hopelessly into a trap. A wheeled vehicle concentrates all its weight onto a few narrow, rolling points, which can easily break through a fragile surface layer. A legged rover, however, spreads that load out, essentially floating over terrain that would swallow its wheeled cousins whole. This design also provides an incredible safety net against one of the most common mission-ending fears, tipping over. On a steep, loose slope covered in gravel or dust, a wheeled rover is constantly fighting a battle against gravity, with a high center of mass that always wants to pull it downhill. A single slip or a wheel digging in too hard can be enough to start a catastrophic roll. A 6-legged machine, by its very anatomy, is incredibly resistant to this. It can always keep at least 3 of its legs on higher, more stable ground, maintaining a perfectly balanced posture even on an incline. This isn't just a theory, it's a principle called static stability, and it means the rover can stop moving at any time, on any slope it can climb, and remain perfectly stable without any active correction. This allows it to take its time, carefully assess its next move, or pause for hours to conduct a delicate scientific measurement without the constant drain of power needed to actively prevent a tip over. The brilliance continues down to the very feet of the machine. Insects don't just have legs, they have an astonishing array of specialized foot designs, each evolved to conquer a specific type of terrain, and this is a treasure trove of ideas for roboticists. For gripping smooth, hard surfaces like rock faces or the exteriors of landers, future rovers could employ foot pads inspired by the millions of microscopic hairs on a gecko's toes that use van der Waals forces to stick to walls without any glue or suction. For loose, sandy soil, feet might mimic the broad, spade-like pads of desert beetles that prevent them from sinking. And for icy worlds like Europa or Enceladus, claw-like tips could dig into the hard frozen surface to provide an anchor, preventing the rover from sliding off into the void. This level of tailored traction means a single rover could be a true all-terrain vehicle, confidently moving from a soft sandy plain to a sheer rocky cliff face without missing a beat. This combination of built-in stability and adaptive traction creates a platform so reliable that it fundamentally changes the kind of science we can do, allowing us to place our most sensitive instruments in places we previously could only observe from a safe and frustrating distance. This ability to conquer the landscape is where the true magic of insect-inspired design comes alive. It's one thing to walk efficiently on flat ground, but the real test of an explorer is what happens when the path forward is blocked. This is the moment where wheeled rovers must stop, recalculate, and often turn back. But for an insect and for a rover built in its image, an obstacle isn't a dead end, it's an invitation. Their multi-legged design, with its independent, articulated limbs, turns navigation into a form of three-dimensional problem-solving. Each leg can be placed with pinpoint precision, probing for a secure foothold on a rocky outcrop or gently testing the stability of a soil patch before committing weight. This is a level of environmental interaction and conscious decision-making that a spinning wheel simply cannot achieve. Imagine a field of large, jagged boulders left over from an ancient asteroid impact. A wheeled rover would see this as an impenetrable maze, a high-risk area to be avoided at all costs. A legged rover, however, would see a staircase. It could methodically lift a front leg, place its foot on top of the first rock, apply pressure to ensure it's stable, and then use that elevated position as a new base from which to hoist the rest of its body up and over. It can cross wide cracks by bracing its body between the two sides, essentially doing the robotic equivalent of chimney climbing. This isn't just mobility, it's terrain assimilation, allowing the machine to become part of the landscape it's traversing in order to master it. This opens up an entirely new catalogue of scientific destinations that have until now been tantalizingly out of reach. The steep, layered interior walls of Martian craters are like a historical record book of the planet's climate, with each stratum telling a story of a different era. Current rovers can only observe these cliffs from a safe distance at the bottom. A legged rover could walk right up to them, using its limbs to anchor itself to the incline, and bring its science instruments directly to the most interesting layers to conduct close-up analysis. Even more exciting is the potential to explore lava tubes and cave networks. These sheltered underground environments are considered one of the most promising places to search for evidence of past or present extraterrestrial life, as they are protected from the harsh surface radiation and extreme temperature swings. A nimble, legged robot could be lowered into a cave entrance and become our first true subterranean explorer on another world, navigating the rocky, chaotic floors of these pristine environments. The ultimate expression of this agility might be found on worlds with dramatic verticality, like the icy cliffs of Mars or the fractured chaos terrains of Jupiter's moon Europa. Here, the ability to climb isn't just a bonus feature, it's an absolute necessity for accessing the most scientifically valuable material. By faithfully mimicking the agility and adaptive movement strategies of insects, we are essentially building keys to unlock these previously forbidden doors. This capability transforms our robotic explorers from distant observers into intimate investigators, finally giving us the tools to touch, sample, and understand the most compelling and secrets of our solar system. This inherent resilience is a cornerstone of insect design, and it points to one of the most critical advantages for a deep space mission: built-in fault tolerance. In the unforgiving environment of space, a million miles from the nearest repair shop, a single mechanical failure can't be the end of the story. Insects understand this principle perfectly. Watch a grasshopper that has lost a leg in a close call with a predator. It doesn't simply collapse. its nervous system instantly recalibrates, shifting its center of balance and adopting a new, slightly altered gait that allows it to keep moving, to keep surviving. This isn't a graceful, perfect walk. It's a limping, adaptive, and brilliantly effective workaround. That ability to accept damage and persist is exactly the kind of robustness we need to engineer into our planetary explorers. For a legged rover, this biological strategy translates into a powerful form of mechanical redundancy. A traditional six-wheeled rover might have a drive system where the failure of a single motor in one wheel could cripple the entire vehicle or, at the very least, severely limit its mobility. But a machine with 6 or 8 independent legs is designed with spare capacity. If one leg is damaged, perhaps a joint freezes from the extreme cold, a motor burns out, or a leg is snapped off by a sharp rock impact, the rover's onboard intelligence can follow the insect's playbook. It would first diagnose the problem, identifying which limb is out of commission. Then, its control algorithms would compute a new, stable gait pattern on the fly, redistributing its weight and movement commands among the remaining healthy legs. The rover might transition from a standard alternating tripod gait to a slower, more deliberate four-legged crawl, or even a hopping motion if the situation called for it. This isn't just a theory. Roboticists are already testing and proving these concepts in labs with hexapod robots that can successfully adapt to losing 2 or even 3 limbs and still make forward progress. This level of resilience is transformative for mission planning. It means that an accident on day 1000 of a mission doesn't have to spell its end. The rover could enter a limp mode, its scientific capabilities perhaps slightly reduced, but its core mission of exploration and discovery would continue. This fault tolerance directly maximizes the return on the immense investment of these missions, ensuring that a billion-dollar spacecraft can deliver science for years beyond its intended lifespan, simply because it was built to be tough, adaptive, and a little bit more like the hardy creatures that have thrived on Earth for eons. This philosophy of designing for survival in the harshest conditions makes redundancy a non-negotiable feature, not just an optional bonus. Every component, from individual leg actuators to the central processing units, can be cross-linked and backed up. Power can be rerouted, data can take alternative paths through the system, and critical functions can have duplicates waiting in the wings. This systemic robustness, inspired by the decentralized and adaptive networks found in nature, creates a machine that is far greater than the sum of its parts. It's a machine that expects things to go wrong and has a plan B, C, and D ready to deploy, ensuring that the singular goal of the mission, to explore and discover, is never compromised by a single point of failure. This inherent toughness, borrowed directly from nature's most resilient engineers, is what will allow our robotic ambassadors to become truly long-term inhabitants of other worlds. But to truly move with the confidence and grace of an insect, a rover needs more than just strong legs. It needs a sophisticated nervous system. It needs to perceive the world not as a series of flat images, but as a rich, three-dimensional tapestry of textures, slopes, and potential hazards. This is where the next layer of insect inspiration becomes absolutely critical: sensor integration and environmental awareness. Insects are walking sensor suites. Their entire bodies are covered in specialized equipment designed to gather real-time data. Delicate antennae constantly sample the air for chemical signatures. Compound eyes provide a nearly 360-degree view of their surroundings, and microscopic hairs on their exoskeleton are sensitive to the slightest changes in air pressure or vibration. This constant, multimodal stream of information is processed on the fly by a remarkably efficient brain, allowing them to make split-second decisions, dodging a predator, finding a foothold, or following a scent trail, all without any outside help. Future rovers can and must emulate this holistic approach to perception. Instead of relying on a few primary cameras, an insect-inspired rover will be covered in a distributed network of sensors, creating a continuous sense of touch for the entire machine. High-resolution stereo cameras would act like compound eyes, building a detailed depth map of the terrain ahead. LIDAR, which stands for light detection and ranging, would fire laser pulses to accurately measure distances and map out the topography in precise detail, even in low light or dust storms. But the most revolutionary addition would be tactile sensors. Imagine each foot of the rover being equipped with sensitive pads that can feel the ground it's about to step on. Just before placing its weight down, it could gently probe the soil to assess its firmness, detecting whether it's stable rock or treacherous, loose sand that might give way. This would allow the rover to make intelligent movement decisions in the moment, choosing the safest path without needing to wait 20 minutes for instructions from Earth. This level of enhanced awareness is the key to true autonomy. Right now, our rovers are incredibly intelligent, but they are also remote-controlled in a delayed, step-by-step manner. Drivers on Earth painstakingly analyze images, plot a safe course that might be just a few meters long, and then beam those commands to Mars. The rover then executes that single drive, stops, and sends back new images for the next round of planning. It's a slow, cautious, and entirely necessary process with current technology, but a rover with insect-like sensing could break free from this cycle. Its onboard artificial intelligence, fed by this rich sensor data, could perceive a field of boulders, identify the optimal path through it in real time, and carefully pick its way across completely on its own. It could see a dust storm approaching on the horizon and autonomously decide to seek shelter behind a large rock. This independence would supercharge exploration, allowing the rover to cover more ground, react to immediate opportunities, and ultimately make its own scientific discoveries without human micromanagement. By giving our machines the senses to truly understand their environment, we are not just building better tools, we are creating intelligent partners in exploration. This entire journey we've been on, from the limitations of wheels to the incredible potential of legs, is part of a much broader and more profound shift in how we approach engineering. It's a philosophy known as biomimicry, a term that literally means to imitate life. Instead of seeing nature as something to be conquered or simply a source of raw materials, biomimicry approaches the natural world as the most experienced and brilliant research and development department on the planet, one that has been solving complex design problems for billions of years. It's about humility and wisdom, recognizing that the solutions to our greatest technological challenges may have already been invented, refined, and perfected by evolution. We just have to be willing to look closely and learn. And when we turn that biomimetic lens towards the challenge of space mobility, the insect world reveals itself as an endless treasure trove of ready-made innovations. Every fascinating adaptation we see is a potential blueprint. The gecko's remarkable ability to scale a perfectly smooth pane of glass isn't magic, it's physics. Its feet are covered in billions of microscopic hairs that create a molecular attraction strong enough to support its weight, a phenomenon known as van der Waals forces. For a rover destined for an asteroid or a rocky cliff face, this same principle could be engineered into gripping feet, allowing it to anchor itself securely in microgravity or on vertical surfaces without any clunky mechanisms. Similarly, the cockroach's infamous and lightning-fast escape response is a masterclass in rapid sensor processing and actuation. Its nervous system is wired for survival, taking in data from its antennae and eyes and converting it into evasive action in milliseconds. This kind of rapid, reflexive stability control could be programmed into a rover's brain, allowing it to instantly correct a slip on loose gravel or react to a small rock slide without a moment's hesitation. The power of this approach is that it allows engineers to leapfrog years of tedious trial and error. Evolution has already done the hard work of testing countless prototypes. The successful designs are the ones still around today. By reverse engineering these biological successes, we aren't just copying shapes, we're uncovering fundamental principles of movement, efficiency, and resilience. We study the precise angle of a joint in a beetle's leg to understand how it achieves such powerful leverage with minimal muscle effort. We analyze the material composition of an ant's exoskeleton to learn how it remains both incredibly lightweight and astonishingly durable. We decode the neural circuits of a centipede to understand how it coordinates dozens of limbs without any traffic jams. This process of biological translation is accelerating innovation at a breathtaking pace, providing us with a library of proven strategies that are perfectly suited for the harsh and unpredictable environments we find on other worlds. This isn't just theoretical, it's already happening in labs and testing facilities around the globe. A brilliant example is NAS, a limbed excursion mechanical utility robot, or LEMUR. Originally developed as a maintenance robot for the International Space Station, LEMUR evolved into a cliff-climbing explorer. Its most striking feature is its 4 limbs, each ending in a foot equipped with hundreds of tiny, fishhook-like claws. This design allows it to grip onto rough, rocky surfaces much like a spider or an insect would, enabling it to scale vertical rock faces that would be completely impossible for any wheeled vehicle. During field tests in the rocky deserts of California, LEMUR successfully used its AI and gripping feet to navigate treacherous terrain, autonomously finding hand and foot holds while scanning the rock for signs of ancient fossilized life. It stands as a powerful, tangible proof of concept that the principles of biomimicry aren't just science fiction. They are the practical, actionable tools that are building the next generation of interstellar pioneers. By embracing the wisdom of the natural world, we are not only accelerating our path to the stars but also ensuring that the machines we send are more graceful, capable, and resilient than anything we've ever built before. While the entire insect world is a source of inspiration, a few standout species have captured the particular attention of roboticists for their almost superhuman, or rather super insect, abilities. These creatures aren't just good at what they do, they are the undisputed champions of their respective survival skills, and each one offers a masterclass in a different aspect of exploration. By breaking down the specific genius of ants, cockroaches, and beetles, we can see exactly which traits engineers are most eager to borrow for the next wave of interstellar robots. Let's start with the ant, nature's ultimate team player and logistics expert. An ant colony operates with a level of coordination and collective intelligence that puts most human organizations to shame. Individually, an ant is impressive. It can lift many times its body weight and navigate back to its nest across complex terrain using path integration, a kind of internal dead reckoning that tracks distance and direction from home. But the real magic happens when they work together. When an ant finds a food source too large for one individual, it doesn't just give up. It recruits a team, and through a series of subtle pushes and pulls, a group of ants will collectively lift and transport an object that is massively disproportionate to their size, navigating obstacles as a single, coordinated unit. For space exploration, this principle of cooperative transport is revolutionary. Imagine a future mission that doesn't send one large, expensive rover, but instead deploys a swarm of smaller, ant-inspired robots. One of these smaller units might find a scientifically priceless rock sample that is too heavy for it to lift alone. Instead of abandoning it, the robot could call over its companions, and together, using simple rules of coordination much like an ant colony, they could collectively move the sample to a central collection point or even back to a lander. This approach offers incredible redundancy. If one small unit fails, the mission continues unimpeded. It also allows for the exploration of a much wider area simultaneously, turning a single landing site into a hub of widespread collaborative science. Then we have the cockroach, an insect often met with a shriek of disgust here on Earth, but in the lab, it's met with awe and respect from engineers. The cockroach is a masterpiece of durability and high-speed navigation in chaotic environments. Its exoskeleton is not just a suit of armor. It's a flexible, articulated shield that allows it to compress its body to squeeze through incredibly narrow cracks, a trait that could be vital for accessing subterranean crevices on other planets. But its most famous trick is its escape response. When threatened, a cockroach can accelerate to incredible speeds in milliseconds, darting under cover and navigating a cluttered floor, full of chairs, shoes, and other obstacles without slowing down to consciously think about its path. It does this through a combination of highly sensitive antennae that act as collision detectors and a nervous system that prioritizes reflex over complex computation. For a rover, this translates into an unparalleled ability for rapid hazard avoidance. A wheeled rover that starts to slip on a slope might take seconds to detect the problem, analyze it, and attempt a correction often too late. A cockroach-inspired rover, equipped with fast-acting contact sensors on its limbs, could feel the beginnings of a rockslide or a wheel sinking into sand and execute an instantaneous reflexive correction, perhaps by jumping to the side or digging its other legs in for stability. This isn't about being skittish. It's about having a lightning-fast emergency response system that prioritizes survival above all else, ensuring the robot lives to explore another day. Finally, we have the beetles, a fantastically diverse family that offers a toolkit of specialized solutions. From the powerful, digging legs of the dung beetle to the incredible water-capturing shell of the Namib desert beetle, each species is a lesson in adapting to a specific niche. But perhaps the most space-relevant of all is the humble dung beetle's relationship with the sky. This industrious insect, after carefully sculpting its prized ball of dung, must roll it in a perfectly straight line away from the competitive chaos of the dung pile. To do this on moonless nights, it has evolved the ability to navigate by the faint, shimmering band of the Milky Way, using the stars to maintain a true course. This celestial navigation is a stunning example of a simple, low-power, and highly reliable guidance system. For a rover on another world, where GPS satellites don't exist and magnetic fields might be unreliable or non-existent, this offers a beautiful alternative. A rover could be equipped with a simple star tracker, a small camera that looks up at the sky to identify constellations, and use them to triangulate its exact position and orientation on the planetary surface. This would provide a fail-safe navigation method that doesn't rely on constant communication with Earth or intricate internal gyroscopes that can drift over time. By studying these three insect archetypes, the cooperative ant, the resilient cockroach, and the celestial navigating beetle, engineers aren't just building a better robot. They are assembling a portfolio of proven biological strategies, each one a key that unlocks a different challenge of the alien landscape. The leap from biological inspiration to a functional, mission-ready machine is already underway in laboratories and research centers across the globe, where the theoretical advantages of insect-like locomotion are being put to the test in a growing family of remarkable prototypes. Leading the charge is the European Space Agency with its fascinating Space Hopper robot. This three-legged, triangular-shaped machine is specifically designed for the daunting challenge of microgravity environments, like those found on small asteroids or moons. Unlike a rover that drives, Space Hopper uses a completely different strategy. It hops. Its 3 legs work in concert to launch the robot across the surface, where it then uses reaction wheels to reorient its body mid-flight and ensure it lands precisely on its feet, ready for the next jump. This hopping gait is a direct mimicry of how some insects, like certain species of spider or grasshopper, navigate unpredictable terrain, making enormous leaps and maintaining perfect control upon landing. The project is a powerful demonstration that mobility on other worlds doesn't have to mean rolling. It can mean leaping, bounding, and stepping with purpose. Beyond major space agencies, the academic world is a hotbed of innovation for hexapod robots. At institutions like ETH Zurich in Switzerland and numerous universities across the United States and Japan, researchers are building and testing multi-legged machines with names that sound like they're from a science fiction novel. These robots are the essential testbeds for the complex algorithms that will one day guide a rover on Mars. Engineers program them with a library of different gaits, a slow, deliberate crawl for tricky sections, a faster, wave-like walking motion for flat ground, and even a running trot for covering distance efficiently. The real magic happens when these robots are let loose in simulated extraterrestrial environments. They navigate through large sandboxes filled with materials designed to mimic Martian regolith, climb over fields of jagged volcanic rock, and attempt to scale steep, crumbly inclines inside vast testing arenas, all while a bank of computers records every slip, every step, and every success. The results from these tests are not just promising, they are often astounding. Where a wheeled test vehicle might struggle, dig in, and become stuck in a sand trap, a hexapod robot will methodically test the ground with a delicate foot, adjust its weight distribution, and choose a more stable path, often using a scrambling, climbing motion that looks eerily like a crab navigating a beach. Some advanced prototypes have demonstrated the ability to confidently climb slopes steeper than 45 degrees, an angle that would be completely insurmountable for any current wheeled rover, and would likely result in a catastrophic tip over. Others have shown incredible resilience by continuing to move and complete objectives, even after suffering a simulated leg failure, automatically recalibrating their gait to limp forward on their remaining 5 limbs. This isn't just incremental improvement, it's a fundamental paradigm shift in mobility, proving that the core concepts borrowed from insects don't just work on paper, they work in the dirt and dust where it matters most. Each successful test is a critical data point, paving the way from the laboratory sandbox to the actual sands of another world, bringing these extraordinary biological concepts closer to reality with every step they take. Of course, the incredible potential of these insect-inspired machines is matched only by the immense engineering challenges they present. Transitioning from a proven, relatively simple wheel to a complex, multi-limbed walking system introduces a whole new universe of design hurdles that must be solved before these robots can confidently take their first steps on another world. The most immediate and obvious challenge is sheer complexity. A simple wheel requires just one motor to spin it, but a single, functional robotic leg might require 3, 4, or even more individual actuators, essentially robotic muscles, to control each joint for hip, knee, and ankle movement, allowing it to lift, swing forward, and place its foot with precision. Now multiply that by 6 or 8 legs. Suddenly, you're dealing with 24 or more motors, each needing its own power supply, control circuitry, and protective housing. This exponential increase in moving parts doesn't just add weight, it introduces countless new potential points of failure. Every joint, every gear, every wire is a component that must withstand the violent vibrations of launch, the vacuum of space, and the harsh conditions on the surface of another planet. This complexity cascades directly into the rover's electronic brain. A wheeled rover's driving algorithm is in principle relatively straightforward. Send more power to the left or right wheels to turn. But controlling a walking machine is a computational nightmare that requires incredibly sophisticated software. The rover's computer must process a constant flood of data from its sensors, cameras, LiDAR, foot pressure sensors, and use it to calculate in real time the exact position, angle, and force for every single one of those 24 actuators, all while maintaining perfect balance and avoiding obstacles. It's the difference between the mental focus required to ride a bicycle in a straight line and the intense, split-second coordination of a parkour athlete running across a series of collapsing rooftops. This demands immense processing power, which in turn consumes more of the rover's most precious resource, energy. Managing this power budget is a critical tightrope walk. More actuators mean more motors to power, and a more powerful computer brain also draws more electricity. Engineers are therefore locked in a constant battle between making the rover capable enough to walk and making it efficient enough to actually survive for a meaningful mission duration on its limited battery or nuclear power source. And then there's the environment itself, which is actively hostile to complex machinery. The temperature swings on a place like Mars can be 200 degrees Fahrenheit between day and night, causing metal and composite materials to expand and contract dramatically, potentially jamming delicate joints or fracturing components. Fine, abrasive dust, the same kind that ended the Spirit rover's mission, is an even greater threat to a legged system. It could easily work its way into the intricate actuators of every joint, grinding away at gears and seizing up motors, effectively paralyzing the robot. On worlds like Europa, the surface is a deep freeze of solid ice bathed in intense radiation from Jupiter's magnetic field, which can slowly degrade electronics and fry sensitive computer brains. Designing a machine that is simultaneously agile, strong, lightweight, power-efficient, dust-proof, radiation-hardened, and capable of operating across a temperature range that would shatter most metals is perhaps one of the most difficult engineering puzzles ever attempted. It requires a complete rethinking of materials, from advanced composites and shape memory alloys that can flex without fatigue, to novel lubricants that won't evaporate in a vacuum or freeze solid in the cold. Yet, for every daunting challenge, a wave of innovation is rising to meet it. The field of materials science is delivering incredible new solutions, like self-lubricating polymers and metal alloys with memory that can return to their original shape after being bent, which could be used in legs to absorb impact. Artificial intelligence is becoming more powerful and, crucially, more energy efficient, allowing for the complex gate calculations to be done with less electrical drain. Engineers are also getting creative with the designs themselves, exploring concepts like hybrid wheel leg systems for flat terrain, or using clever mechanical linkages to reduce the number of actuators needed per leg. The path forward isn't about finding a single magic bullet, but rather about 1,000 tiny breakthroughs across different fields of engineering, all converging to make the dream of a walking rover not just a fascinating prototype in a lab, but a reliable, mission-ready reality. Overcoming these obstacles is the essential final step in unlocking a new era of exploration, one where our machines are finally agile and tough enough to go wherever the most compelling science awaits. This incredible versatility is where the true power of the legged rover concept truly shines, because our solar system is not a single, uniform environment. It's a spectacularly diverse collection of worlds, each with its own unique set of geological puzzles and gravitational rules. The beauty of an insect-inspired design is its ability to adapt to this entire spectrum of challenges, making it the ultimate all-terrain vehicle for the cosmos. Let's start with the smallest and most treacherous of these destinations, asteroids. These rocky or metallic bodies are often little more than piles of rubble held together by the faintest whisper of gravity. Sending a traditional rover to an asteroid is almost unthinkable. A wheeled vehicle would have virtually no traction. The moment it tried to move, it would likely just spin its wheels, kicking up dust and pebbles and potentially launching itself right off the surface and back into space. But a legged rover is perfectly suited for this microgravity environment. Its legs wouldn't just be for walking, they would act as sophisticated anchoring systems. Imagine a robot carefully approaching the asteroid, then using its limbs to gently latch onto a large boulder, much like a spider securing itself to a wall. Each foot could be equipped with a microspine gripper, a system covered in dozens of tiny, sharp hooks that snag onto the smallest asperities in the rock, allowing the rover to hold on firmly without needing any downward force from gravity. Once anchored, it could use its other legs to carefully move across the surface, sampling different materials or even drilling into the asteroid to understand its composition. This capability is critical, as asteroids are considered time capsules from the early solar system, holding clues to the formation of planets and possibly even the organic ingredients that led to life on Earth. A legged explorer could be the key to unlocking those secrets. Then we have the icy moons, like Jupiter's Europa or Saturn's Enceladus worlds, that have captured the imagination of scientists like no other. These are not barren rocks. They are active, ocean-bearing satellites covered in a global shell of ice, cracked and jumbled by the immense gravitational forces of their giant parent planets. The surface of Europa is a chaotic nightmare for a wheeled vehicle. Vast, slick plains of ice cross-cut by deep fissures and littered with house-sized blocks of ice that have been churned up from below. Here, traction is everything. A wheel would simply spin hopelessly on the smooth, hard ice, but an insect-inspired rover, perhaps modeled after a beetle or a fly that can walk on a wet pane of glass, would use a completely different strategy. Its feet could be equipped with innovative adhesive pads or crampon-like claws that bite into the ice, providing a secure grip with every step. This would allow it to carefully descend into the very cracks and fissures that are so scientifically compelling, because it is from these openings that plumes of subsurface ocean water are known to erupt, venting material from the hidden sea below directly into space. A legged robot could be the first machine to directly sample this material right at the source, potentially detecting complex organic molecules or even signs of biological activity without ever having to drill through miles of ice. It could walk right up to the edge of a vent, reach out a leg to collect a fresh sample, and bring it back to a suite of onboard instruments, becoming our first direct explorer of a potentially habitable environment beyond Earth. And of course, there's Mars, a world we know well, but one that still holds its most profound secrets just out of reach of our current rovers. The red planet's varied topography is a tale of two extremes: vast, smooth plains that are easy driving, and incredibly alluring, rugged highlands that are currently no-go zones. The most exciting geology, the ancient river deltas, the steep cliffs where layers of history are exposed, the deep, sheltered lava tubes that could have protected ancient microbes from surface radiation, all exist in these difficult-to-reach places. This is where a legged rover transitions from being a useful tool to an absolutely essential one. A machine with the sure-footedness of a mountain goat could finally approach the edge of the 3,000-mile-long Valles Marineris Canyon system and carefully climb down its cliffs, reading the geological history embedded in the rock layers with each step. It could walk to the entrance of a cave, a potential preserve for signs of past life, and navigate the treacherous rubble at its entrance to become our first subterranean explorer on another world. On Mars, the legged rover isn't just about getting from point A to point B. It's about finally being able to touch the rocks that tell the most important stories, to go into the places that have been calling to us for decades, and to conduct the kind of hands-on, detailed science that could answer the ultimate question: did life ever exist beyond our home planet? This adaptability to such wildly different environments, from the microgravity rubble piles of asteroids, to the icy slickness of moons, to the complex, varied landscape of Mars, proves that this isn't just a niche technology. It is the foundational mobility solution for the next era of solar system exploration, a universal key designed to unlock every door we encounter. This incredible freedom of movement, however, creates a monumental new challenge. A machine this agile cannot be remote controlled from Earth. The old model of painstakingly analyzing images for hours to plan a safe, 2-meter path for a wheeled rover simply won't work for a legged explorer that needs to make dozens of delicate, real-time decisions with every single step it takes. To truly function with the grace and independence of an insect, these rovers must be endowed with a sophisticated artificial intelligence that acts as its own onboard brain and nervous system, granting it the gift of true autonomy. This isn't about pre-programmed routes. It's about creating a machine that can perceive, reason, and react to its environment in the moment, completely on its own. The guiding principle for this AI is once again drawn directly from nature. Engineers are studying the surprisingly efficient decision-making processes of insects. A cockroach darting under a cupboard isn't performing complex calculations. It's running on a set of refined instinctual algorithms and reflex loops that process sensory input and generate life-saving movement in a fraction of a second. The goal for rover AI is to mimic this elegant efficiency. Sophisticated algorithms will constantly fuse the torrent of data coming from its camera eyes, LiDAR, and sensitive foot sensors to build a dynamic, three-dimensional map of the world directly in front of it. This map isn't just a picture, it's an intelligent understanding of the terrain. The AI will classify surfaces, identifying stable rock from risky sand, calculating the angle of a slope, and pinpointing the most promising footholds. Then, drawing from a vast internal library of gait patterns, it will choose the optimal movement strategy for the challenge it faces, perhaps a slow, careful climbing gait for a sheer rock face or a faster, scurrying walk across a flat plain. The real magic, however, comes from machine learning. Unlike a pre-programmed machine, an autonomous rover will have the ability to learn from its own experiences and improve its performance over time. Every successful step, every recovered slip, and every navigational choice becomes a data point that the AI uses to refine its internal models. If a particular type of crumbly rock consistently causes its feet to slip, the AI will learn to recognize that rock type visually and adjust its step placement or pressure accordingly the next time it encounters it. This continuous, on-the-job learning means the rover that lands on day one is actually less capable than the veteran explorer it will become after months on the surface, having adapted its skills specifically to the unique quirks and challenges of its new planetary home. This shift to autonomy is absolutely critical for overcoming one of the most fundamental constraints of deep space exploration: the speed of light. The communication delay between Earth and Mars can vary from 4 to 24 minutes one way. Waiting 40 minutes to hear back from mission control after sending a single image is simply not feasible for a rover that needs to decide where to place its foot in the next half-second. By handing over the immediate decision-making to the rover itself, we eliminate these debilitating delays. The rover becomes a self-sufficient field scientist. It could independently spot an unusual, layered rock formation glinting in the sun, make the executive decision that it warrants investigation, and then autonomously plot and execute a complex path across difficult terrain to reach it, all without ever checking in with home. It could sense a sudden drop in air pressure indicating an approaching dust storm and immediately seek out the best available shelter. This level of independence doesn't just make exploration faster, it makes it smarter, more responsive, and infinitely more capable, transforming our robotic ambassador from a passive tool into a true partner in discovery. As artificial intelligence continues its rapid evolution, the cognitive abilities of these legged rovers will grow in lockstep, allowing them to undertake increasingly complex missions and make ever more nuanced scientific judgments on our behalf. But before any legged rover can take its first historic step on another world, it must first prove its worth in some of the most demanding proving grounds right here on Earth. The journey from a brilliant concept in a robotics lab to a trusted piece of flight hardware is a long and arduous one, paved with relentless testing and validation. This critical phase is where these insect-inspired machines face simulated versions of the extreme challenges they will encounter millions of miles from home, ensuring that when they finally arrive, they are ready for anything. This process begins in specialized facilities designed to replicate, as closely as possible, the alien conditions of other worlds. At NASA Jet Propulsion Laboratory, for instance, you'll find the Mars Yard, a large, enclosed area filled with tons of reddish sand, rocks, and slopes, all carefully curated to mimic the texture, composition, and behavior of genuine Martian regolith. This is where early prototypes of legged robots are put through their paces. Engineers watch intently as the machine attempts to climb a 30-degree incline of loose sand, its legs digging in and scrambling for purchase. They observe how its feet sink into the fine material, measuring the power draw from each actuator as it works to pull a leg free for the next step. Every stumble, every successful climb, and every instance of slipping is captured on high-speed cameras and fed into computer models, providing a treasure trove of data that informs the next design iteration. It's in this sandy arena that theoretical advantages meet practical reality, and where the elegant gate algorithms developed in simulation are stress-tested against the beautiful, unpredictable chaos of the real world. Beyond these terrestrial landscapes, the testing gets even more extreme. To simulate the airless, freezing conditions of an asteroid or the surface of the moon, engineers use massive thermal vacuum chambers. Inside these gleaming steel cylinders, a legged rover prototype is subjected to the brutal combination of a hard vacuum sucking out all the air to simulate space and dramatic temperature cycles. Banks of powerful lamps simulate the unforgiving heat of direct sunlight, while liquid nitrogen circulating through the chamber walls creates the deep cold of shadow. Here, the rover isn't just tested for its mobility, it's tested for its very survival. Engineers check that its motors don't overheat without air to cool them, that its lubricants don't evaporate or freeze solid, and that its composite limbs don't become brittle and crack under the intense thermal strain. They test its delicate sensors to ensure they can still function accurately in these punishing conditions. This rigorous environmental testing is what separates a fascinating laboratory experiment from a machine that can be trusted with a multi-billion-dollar mission. The philosophy behind this entire exhaustive process is one of iterative refinement. Each test campaign is designed to find the weaknesses, the unforeseen failures, and the design oversights. A foot designed for hard rock might perform poorly in deep dust, prompting a redesign with a broader, more paddle-like shape. A particular walking gait might work perfectly on flat ground, but cause the rover to become unstable on a side slope, leading software engineers to develop a new, more stable algorithm for traversing cross slopes. This cycle of test, analyze, redesign, and retest continues over and over, each time hardening the design against the realities of space. It's a process that demands humility, because it repeatedly shows that even our best ideas often need adjustment when faced with the complex physics of an alien environment. This meticulous, often grueling work is the unsung hero of space exploration, the essential, behind-the-scenes effort that builds the unshakable confidence required to finally say, "This machine is ready for launch." And while the incredible agility and resilience of legged locomotion might be the most visually striking application of insect inspiration, the influence of these tiny creatures extends far deeper into the very architecture of a future rover, touching systems that have nothing to do with movement at all. This is the true power of a holistic biomimetic approach. It's not just about building a robot that walks like a bug. It's about reimagining the entire machine to operate with the integrated, hyper-efficient, and brilliantly communicative logic of a living organism. By looking beyond just the legs, engineers are finding that insects offer a masterclass in everything from power management and communication to the very philosophy of collective intelligence. Consider the monumental challenge of communication and coordination for a future mission that doesn't involve a single, large rover, but an entire fleet of smaller, collaborative robots. How do you prevent these machines from getting in each other's way, or worse, all converging on the same uninteresting patch of ground, while ignoring a truly spectacular discovery just over the next hill? For this, we can look to the humble ant and its use of pheromone trails. An ant doesn't need a complex radio or a detailed map to tell its colonymates where to find food. It simply lays down an invisible chemical trail on its return journey, a path that other ants can choose to follow and reinforce if the food source is good, or that will naturally evaporate if it leads to a dead end. This creates a simple, elegant, and incredibly efficient decentralized communication network. Engineers are now developing digital versions of this concept for robot swarms. Instead of chemical pheromones, a rover could leave behind a virtual trail, a low-power, short-range radio signal, or even a series of subtle visual markers that indicates the path it has taken and the value of what it found. Other rovers in the swarm could detect these signals, and their onboard AI would decide whether to follow the trail to a promising area or to strike out in a new direction to explore uncharted territory. This creates a self-organizing system where the robots collectively and efficiently map an area without any central controller, constantly adapting their search pattern based on real-time discoveries, just like an ant colony efficiently harvesting food from the most productive sources. The lessons from insect biology also extend deep into the rover's internal systems, particularly its metabolism, or in engineering terms, its power management and thermal regulation. An insect is a paragon of energy efficiency. Its entire body is designed to perform incredible feats while consuming minuscule amounts of power derived from its last meal. Its exoskeleton provides structural support without the high energy cost of an internal skeleton powered by constantly firing muscles. Its nervous system is optimized for rapid, low-power reflexes rather than energy-hungry, conscious thought. For a space rover, which is fundamentally a machine built around the constraints of a limited power budget, these principles are a guiding light. Engineers are exploring designs that mimic this metabolic efficiency by using passive systems wherever possible. For thermal regulation, instead of power-draining electric heaters, a rover might use a circulatory system of pipes filled with a wax that melts and solidifies at specific temperatures, absorbing excess heat during the day and slowly releasing it during the cold night, much like an insect's body manages its temperature through behavioral and physiological adaptations. Power could be managed with a similar biological mindset, putting non-essential systems into a deep, torpor-like sleep state during periods of inactivity, only waking them when absolutely necessary to conserve every precious joule of energy for mobility and science. This shift in thinking from seeing a rover as a collection of power-hungry components to viewing it as an integrated, energy-conscious organism could dramatically extend mission lifetimes and enable more ambitious science operations within the same strict power constraints. This holistic approach culminates in the concept of the rover as a complete, bio-inspired entity. Every system, from its legs and sensors to its communication protocols and power management, is co-designed to work in harmony, much like the interdependent systems in an insect's body. The flexibility of its limbs could be used not just for walking, but to orient its solar panels toward the sun for optimal power generation, or to position its body as a communications relay antenna for other rovers. Waste heat from its computer brain could be scavenged and piped to keep sensitive instruments warm at night. By adopting this fully integrated, organism-level design philosophy, inspired by millions of years of evolutionary optimization, engineers are moving beyond building mere machines. They are creating synthetic explorers, resilient, efficient, and adaptable beings capable of surviving and thriving in environments that are otherwise utterly hostile to life as we know it. This vision of a collaborative robotic fleet takes its most powerful form in the concept of swarm robotics, a field directly inspired by the mesmerizing collective behavior of social insects. An ant colony or a beehive is far more than just a collection of individuals. It's a superorganism, a single entity composed of many simple parts that together exhibit a form of collective intelligence known as swarm intelligence. No single ant is in charge. There is no central command issuing orders. Instead, each ant follows a simple set of rules based on local information. If you find food, lay a pheromone trail back to the nest. If you encounter a strong pheromone trail, follow it. From these incredibly basic interactions emerges a highly adaptive, resilient, and efficient system that can solve complex problems like finding the shortest path to a food source or allocating the right number of workers to defend the nest. This is the profound insight that swarm robotics seeks to harness. That complexity and intelligence can arise from simplicity and local cooperation without any need for a complicated, fragile, and power-hungry central brain. Applying this to space exploration opens up a revolutionary new mission architecture. Instead of sending one large, incredibly expensive, and singularly vulnerable rover, we could deploy a swarm of dozens of smaller, simpler, and cheaper insect-inspired robots from a single lander. These machines wouldn't be programmed with a detailed, step-by-step map of what to do. Instead, they would be given a high-level goal: map this crater, or find the highest concentration of a specific mineral, and a set of simple rules for how to interact with each other and their environment to achieve it. They would spread out across the landscape, each one an independent explorer. Their constant, short-range communication with their nearest neighbors would create a dynamic, living network, a kind of mobile internet that allows the swarm to share data and coordinate its actions in real time. If one rover made a fascinating discovery, like a strange mineral formation, that information would ripple through the swarm, causing other robots to adjust their paths and converge on the site to conduct their own complementary analyses, creating a multi-perspective scientific investigation without any instruction from Earth. The advantages of this approach are transformative. Redundancy is built into its very core. In a traditional mission, the failure of a single key component on one rover can end the entire mission. In a swarm, the loss of several individual robots is a manageable setback, not a catastrophe. The swarm simply reconfigures itself around the gap, and the mission continues unabated. This approach also supercharges data collection. A single rover can only be in one place at one time, providing a single data point. A swarm of 20 rovers can be in 20 places at once, conducting simultaneous measurements across a wide area, allowing scientists to understand the spatial relationships and variations in the environment in a way that is currently impossible. One rover might specialize in being a communication hub, positioning itself on a high point to act as a relay between the swarm and the orbiting satellite that sends data back to Earth. Others might be equipped with microscopic imagers to study fine-grained soil textures, while others carry spectrometers to analyze rock composition. They could work together to perform physically complex tasks, like collectively dragging a heavy instrument package up a slope or forming a phased array of antennas to boost their signal strength back to Earth. This isn't just an incremental improvement on how we explore. It's a fundamental shift from sending a lone adventurer to deploying an entire, intelligent field team, capable of covering vast territories and supporting each other in ways that dramatically increase the scientific yield and robustness of every single mission we launch. Perhaps the most compelling argument for this shift in design philosophy lies not just in the spectacular science it enables, but in the cold, hard calculus of economics and logistics. Space exploration is by its very nature an incredibly expensive endeavor, where every single gram launched from Earth carries a staggering price tag, and every day of operation is a precious commodity. It is here that the insect-inspired rover reveals perhaps its most revolutionary advantage: the potential to deliver unparalleled scientific return on investment, fundamentally changing the economic model for how we explore our solar system. The savings begin with the most critical factor in any launch mass. While a legged system is mechanically more complex than a set of wheels, its overall architecture can lead to a significantly lighter vehicle. This is because a single, multi-functional legged rover can replace the need for multiple specialized vehicles. Consider a hypothetical mission to a place with diverse terrain, like the Martian polar regions. Today, we might need to design one rover capable of crossing flat plains, a separate drone to scout cliffs, and perhaps even a stationary lander for detailed analysis. A single, highly agile legged rover, however, could fulfill all those roles itself. Its legs allow it to traverse the flats, climb the icy cliffs to access layered deposits, and use its limbs to stabilize itself as a stationary platform for sensitive measurements. This consolidation of capabilities into one chassis eliminates the mass penalty of launching multiple systems, their separate power supplies, and their duplicate communication hardware, leading to massive savings right at the launch pad. This inherent durability and resilience we've discussed also translates directly into financial savings. A mission is a catastrophic financial loss if the vehicle fails prematurely. The ability of a legged rover to avoid hazards, tolerate leg failures, and operate for a longer duration dramatically increases the odds of mission success. This higher success rate means that the billions of dollars invested in development, launch, and operations are far more likely to yield their full intended scientific return. Furthermore, a longer operational lifespan means more science per dollar. Every additional day a rover survives on another world is a day of free bonus science, as the immense upfront costs have already been paid. A rover that can operate for years instead of months effectively drives down the daily cost of exploration, allowing agencies to extract exponentially more value from their initial investment. This robustness also reduces the need for overly conservative driving and extensive ground-in-the-loop planning, which consumes thousands of hours of expensive engineering time on Earth. A more autonomous, capable rover can make its own safe choices, freeing up that human capital for deeper scientific analysis and planning future, even more ambitious missions. These economic benefits make biomimetic designs incredibly attractive for space agencies operating under constant budget constraints and for the growing number of commercial entities entering the space sector. A lighter, more capable, and more reliable rover allows for missions to be flown more frequently, to more diverse locations, and with a higher confidence of success. This isn't just about saving money, it's about enabling a new paradigm of sustainable exploration. By maximizing efficiency and return at every step, from design to deployment to operation, we can create a future where exploring the moons of Jupiter or the canyons of Mars isn't a rare, generation-defining event, but a more regular and achievable part of humanity's ongoing journey into the cosmos. This shift towards smarter, more biologically informed engineering is the key to building a lasting and affordable presence throughout the solar system, ensuring that the quest for knowledge can continue for generations to come. Perhaps one of the most profound yet often overlooked impacts of this insect-inspired revolution lies not in the engineering labs or on the Martian surface, but in its incredible power to capture the public's imagination and inspire a new generation. There's something uniquely compelling about blending the utterly alien concept of interplanetary exploration with the deeply familiar wonders of the natural world we see in our own backyards. A six-legged robot climbing a crater wall on Mars isn't just a machine, it becomes a story. It's a narrative that connects the audacious ambition of reaching other worlds with the quiet, resilient genius of a beetle navigating a leaf. This fusion of cutting-edge technology and biological inspiration creates a powerful bridge of understanding, making the incredibly complex field of robotics feel more accessible, more relatable, and far more magical to people who might otherwise see space exploration as something distant and impenetrable. This connection is a potent tool for engagement, one that space agencies and educators are increasingly keen to harness. Educational programs built around biomimicry can transform abstract STEM concepts into tangible, exciting projects. Imagine a classroom where students aren't just learning about gears and motors, but are instead challenged to design their own insect-inspired robot leg to traverse a sandbox Mars yard. They learn about physics through the principle of leverage in a jointed limb, about biology by studying how an ant distributes its weight, and about computer programming as they write simple algorithms for gate patterns. This hands-on, interdisciplinary approach makes learning a dynamic adventure, showing young minds that science isn't a collection of isolated facts in a textbook, but a living, creative process of solving problems by looking at the world around us with curiosity. For a child who is fascinated by bugs, this can be the pivotal moment that reveals a path toward becoming a mechanical engineer, a roboticist, or an astrobiologist. Media coverage plays an equally vital role in shaping this narrative. Documentaries and news features that highlight the creative process behind these rovers, showing the engineers studying slow-motion footage of a running cockroach or testing prototype legs in a bed of gravel, humanize the scientific endeavor. It shifts the public perception from seeing these missions as sterile, impersonal technological deployments to understanding them as the products of intense creativity, collaboration, and a deep sense of wonder. This kind of storytelling fosters a stronger emotional connection and a sense of shared ownership in these incredible journeys of discovery. When people understand the ingenuity and the sheer coolness behind the machine, they are far more likely to become passionate supporters, following every step of the mission and advocating for the continued funding that makes such exploration possible. Ultimately, this broad public engagement is about more than just excitement. It's about building a sustainable foundation for the future of space exploration. Scientific progress relies on public support, which in turn influences political will and funding priorities. By making these missions relatable and demonstrating how they spring from a place of creativity and curiosity, we build a much broader and more durable base of appreciation. This isn't just about inspiring the next generation of scientists. It's about cultivating an informed and enthusiastic public that values scientific innovation as a crucial part of our culture and our future. This widespread support is the essential fuel that will power the ambitious missions of tomorrow, ensuring that the journey of discovery continues to capture our collective imagination and drive us forward. Yet as we embrace this incredible potential to learn from nature, we must also pause to consider the deeper responsibilities that come with it. Biomimicry is not simply a one-way extraction of ideas. It's a form of dialogue with the natural world, and like any dialogue, it requires respect, humility, and a thoughtful approach to the ethical questions it inevitably raises. The core principle is to ensure that in our quest to imitate life, we do so in a way that honors and protects the very systems we are learning from. This means that engineers and designers have a duty to consider the potential for unintended consequences. For instance, if we were to develop a rover with incredibly effective gripping feet inspired by a gecko's adhesive capabilities, we must also ask what would happen if that same technology were to be used in a way that could damage pristine extraterrestrial environments. Could those gripping feet inadvertently scrape away or contaminate delicate, ancient rock formations that hold irreplaceable scientific information about the history of our solar system? The goal is to create technology that is a gentle visitor, not a disruptive force, ensuring that our exploration leaves the most scientifically valuable worlds as undisturbed as possible for future study. This conversation extends beyond physical impact to the very way we acquire biological knowledge. The field of biomimicry relies on intense scientific study of living creatures, often in laboratory settings. This raises important questions about the ethical treatment of the animals we study. Research must be conducted with the utmost respect for their well-being, adhering to strict guidelines that minimize stress and harm. Furthermore, there is a growing discussion about the ethics of knowledge ownership, particularly when drawing inspiration from the biological adaptations of indigenous species. While a specific insect's unique ability may be a source of inspiration for a global space agency, it's crucial to acknowledge the origins of that inspiration and consider frameworks for equitable benefit sharing, ensuring that the natural heritage of a region or community is recognized and respected in the process of technological development. A more profound, almost philosophical ethical layer emerges as our machines become increasingly lifelike. As we design robots that scuttle, climb, and sense their environment with an uncanny resemblance to living insects, we edge into new moral territory. While these machines are, and will remain, sophisticated tools without consciousness, their very form and behavior can evoke empathetic responses from people. This prompts us to consider the ethical guidelines for their deployment and interaction with environments, both on Earth and abroad. On Earth, the use of animal-like robots for surveillance or in military applications demands careful scrutiny and public discourse to establish clear boundaries against misuse. In space, the primary ethical directive is planetary protection, the rigorous international practice of preventing biological contamination of other worlds with Earth life and protecting our own biosphere from potential extraterrestrial material upon return. A robot that looks and moves like an insect, if not sterilized to the most exacting standards, could inadvertently become the most successful invasive species in history, carrying terrestrial microbes to a place like Mars and forever blurring the line between what is native and what is contamination, potentially jeopardizing the entire scientific search for alien life. This intertwining of biological inspiration and ethical responsibility is not a constraint on innovation, but rather its necessary conscience, guiding us toward a future where our technological achievements are as wise and sustainable as they are brilliant and ambitious. Looking ahead, the next evolutionary leap for these insect-inspired explorers won't just be about refining their shape or programming. It will involve fundamentally reimagining what they are made of and how they think. The future lies in the development of smart materials, substances that can actively change their properties in response to their environment. Much like a living insect's exoskeleton can stiffen for support or remain flexible for movement. Imagine a rover leg constructed not from rigid metal or composite, but from a matrix of advanced polymers and alloys engineered to alter their stiffness on command. When navigating a flat, hard plane, the limbs could remain firm and efficient. But upon encountering a treacherous, loose slope, a signal from the rover's brain could trigger a change, causing the material in the feet or lower legs to become slightly softer and more compliant, allowing them to mold themselves to the uneven terrain for superior grip and weight distribution, exactly like an insect adjusting its posture. This isn't fantasy. Research into shape memory alloys and electroactive polymers is already bringing these concepts into the realm of possibility, promising a level of mechanical adaptability we've only seen in nature. This material intelligence will be perfectly paired with a revolution in artificial intelligence, moving beyond the sophisticated autonomy of today into the realm of true cognitive partnership. The goal is to create an AI that doesn't just react to its environment, but anticipates and learns from it in a deeply integrated way. Future rovers will possess what engineers call proprioceptive awareness, a detailed internal sense of their own body's position, the stress on each joint, and the wear on every component, combined with an external understanding of the world built from a constant multi-sensor data stream. Their AI will run incredibly complex simulations in real time, predicting the outcome of a potential step before the leg even moves. It will calculate the precise amount of force needed to grip a rock without cracking it, or the optimal gait to conserve energy while carrying a heavy sample up an incline. This system will learn so thoroughly from its own experiences that it will develop unique behaviors optimized for its specific mission location, becoming a veteran explorer of its own alien world within weeks of landing. Crucially, the manufacturing of these advanced machines will itself be transformed by technologies like 3D printing and nanotechnology. Instead of being assembled from thousands of individually manufactured parts shipped from Earth, a future rover might be printed layer by layer, using a versatile feedstock material that can be programmed to form both rigid structural elements and flexible, sensor-laden skin in the same process. This could allow for incredibly complex, organic-looking designs that are both lighter and stronger than anything built with traditional methods. Even more remarkably, nanotechnology could enable self-repairing structures. A leg scratched by a sharp rock might automatically secrete a nanofluid from embedded reservoirs that hardens to fill the microfracture, much like blood clotting to seal a wound. Or a surface coated with a layer of smart nanoparticles could change its texture on demand, becoming smooth to shed dust or rough to increase friction, creating an adaptive surface that is always optimized for the current conditions. Together, these advancements in materials science, artificial intelligence, and manufacturing will create a new class of explorer that is far more capable, resilient, and independent than anything we have today. They will be machines that can feel their environment, heal from minor damage, and make decisions with a wisdom that borders on instinct. This progress will inevitably blur the line between the biological world that inspires us and the mechanical world we create, leading us to a fascinating new chapter in exploration where our robotic partners become less like tools and more like trusted colleagues, capable of venturing into the most extreme environments with a level of grace and intelligence that we can currently only imagine. This vision of exploration is evolving from one of solitary machines beaming day to back to a distant Earth into something far more dynamic and interactive, a true partnership between human ingenuity and robotic capability. The next great leap won't be taken by robots or astronauts alone, but by teams of both working in concert, each playing to their unique strengths. In this collaborative future, insect-inspired rovers are perfectly poised to become the ultimate companions for human explorers, acting as force multipliers that dramatically enhance both safety and scientific return on other worlds. Their unique blend of agility, autonomy, and resilience makes them not just tools, but trusted partners in the most hostile environments we will ever encounter. Imagine a team of astronauts setting up the first permanent base on the Moon. The landscape outside is a treacherous mix of deep shadow and blinding sunlight, littered with craters and fields of abrasive dust that could shred a spacesuit or damage equipment. Before a human ever steps out to conduct a moonwalk, a small swarm of insect-like scouts would be deployed from an airlock. These nimble machines would fan out across the terrain, their multi-legged design allowing them to scramble over rocks and peer into dark craters with ease. Their mission is to act as an advanced guard, creating a detailed, real-time hazard map of the area. Using their suite of sensors, they would identify patches of unstable ground, map the precise location of sharp outcrops, and even use thermal cameras to find the most stable, well-lit paths for their human partners to follow. They would essentially create a dynamic, living safety net, constantly patrolling the perimeter of the base and alerting the crew to any unforeseen dangers, from a sudden slope failure to the approach of a micrometeoroid shower. This isn't just convenient, it's a fundamental shift in risk management, using robots to absorb the inherent dangers of initial reconnaissance, so that human explorers can focus on the complex work of discovery and construction. The collaboration extends far beyond mere scouting. These robotic partners would become an extension of the crew's own capabilities, acting as telepresent assistants and invaluable fetch and carry units. Picture an astronaut geologist perched on the rim of a magnificent Martian cliff, examining a fascinating layer of sedimentary rock that holds clues to the planet's watery past. A crucial sample is just out of reach, 10 meters down a near-vertical face that is far too dangerous for a human to descend. Instead of risking a perilous climb, the scientist simply gives a high-level command to a waiting legged rover. The machine, with its impeccable balance and gripping feet, nimbly picks its way down the cliff face, its movements guided by its own autonomous hazard avoidance systems but overseen by the human. It reaches the precise spot, uses a tool on its limb to carefully extract the sample, and then climbs back to deliver its prize directly to the astronaut's hand. In this scenario, the human provides the expert judgment, the scientific curiosity, and the overarching goals. The robot provides the physical capability, the access, and the willingness to operate in high-risk zones. Together, they achieve an outcome that would be impossible for either to accomplish alone, merging human intuition with robotic daring. This synergy will be the absolute cornerstone of establishing a sustained, rather than merely a fleeting, presence on the Moon or Mars. Building a habitat, maintaining a power grid, and conducting long-term science is a monumental undertaking that requires a constant cycle of maintenance, resource gathering, and expansion. Insect-inspired robots working in swarms could be the tireless workforce that makes this possible. They could be tasked with the repetitive but vital jobs that would otherwise consume precious crew time and energy. Things like assembling solar panel arrays, connecting modular habitat units, or even mining local regolith for water ice or construction materials. Their ability to work around the clock, untroubled by the need for sleep or protection from radiation, would accelerate progress exponentially. The human crew, freed from these mundane but essential tasks, could then focus on the higher-order work that robots cannot do, making complex decisions, troubleshooting unexpected problems, conducting nuanced scientific experiments, and ultimately, building a community. This division of labor creates a sustainable ecosystem of exploration, where humans and robots are interdependent partners, each doing what they do best to ensure the collective success and longevity of the mission. This collaborative model doesn't replace human explorers. It empowers them, allowing a small crew to achieve the productivity of a much larger team, and finally turning the dream of living on another world into a practical, achievable reality. This shift toward insect-inspired robotics is not happening in isolation within any single nation's borders. It is a truly global movement, uniting space agencies and research institutions around the world in a shared pursuit of a more adaptable future in space exploration. The European Space Agency, or ESA, has been a pioneer in this field with its ambitious Space Hopper program, a clear testament to the international nature of modern scientific development. While managed by ESA, the Space Hopper project is actually driven by a dedicated team of students and researchers at ETH Zurich, one of Switzerland's premier science and technology universities. This collaborative model, blending the oversight of a major space agency with the fresh, innovative energy of an academic institution, is becoming a blueprint for how complex challenges are tackled on a global scale. Across the globe, JAXA, the Japan Aerospace Exploration Agency, brings its own unique cultural and technical perspective to the table. Japan has a long and deep history of advanced robotics and a distinct philosophical appreciation for the natural world, which informs their approach to biomimetic design. Their research into agile, multi-limbed robots for navigating the rugged, unpredictable terrain of asteroids directly complements the work being done in Europe and North America, creating a rich tapestry of parallel development. Meanwhile, CNSA, the China National Space Administration, has dramatically accelerated its space capabilities in recent years, with ambitious lunar exploration programs and plans for a research station on the Moon. Their investment in biomimetic robotics is a strategic move to ensure their future rovers can access the most scientifically valuable and challenging locations on the lunar surface, particularly within the permanently shadowed craters at the poles where water ice is believed to reside. This isn't a race with a single winner. It is a constellation of efforts, each contributing a vital piece to the overall puzzle. The power of this international framework lies in its ability to pool not just financial resources, but perhaps more importantly, intellectual capital and diverse cultural perspectives. A challenge as multifaceted as designing a robot that can walk on another planet benefits enormously from having engineers, biologists, and computer scientists from different backgrounds and with different problem-solving approaches, all working toward a common goal. A team in Germany might excel at precision mechanical engineering for leg joints, while a group in South Korea might lead the way in developing ultra-sensitive tactile sensors for robotic feet. Researchers in the United States could be creating the advanced artificial intelligence algorithms needed for autonomous navigation, while their counterparts in India might focus on creating lightweight, durable composite materials for the rover's body. By sharing data, publishing findings in international journals, and collaborating on joint testing programs, these disparate groups create a collective intelligence that is far greater than the sum of its parts. This collaborative spirit accelerates the pace of innovation dramatically, preventing redundant work and allowing each team to build directly upon the latest breakthroughs from their colleagues overseas. It ensures that the final designs are not just products of a single nation's priorities, but are instead refined by a global conversation about what is most effective, most efficient, and most reliable. Beyond the sheer technical advantages, this cooperative model carries a profound symbolic weight. In a world often divided by terrestrial politics and conflict, the shared, peaceful goal of scientific discovery and space exploration remains one of the most powerful unifying forces available to humanity. A mission to send a biomimetic rover to explore the caves of Mars or the cliffs of an asteroid is not a national project. It is a human project. It represents our collective curiosity, our shared desire to understand our place in the cosmos, and our common hope for a future beyond our own planet. International partnerships on this scale, such as the immensely successful collaboration on the International Space Station, build deep bonds of trust and mutual respect between countries. They require a long-term commitment to communication, transparency, and shared success, fostering a spirit of diplomacy and cooperation that can have positive ripple effects far beyond the space sector. The image of a rover whose design was inspired by life on Earth and whose construction was a global effort, trundling across an alien landscape, is a potent reminder that when we choose to work together, humanity is capable of achieving the extraordinary. This shared progress in science and technology becomes a common language, a bridge between cultures, and a beacon of what is possible when we focus on our shared future among the stars. This long-term vision moves us beyond the concept of single, finite missions and into the realm of permanent, sustainable presence. Insect-inspired rovers are the key workforce for this new era, acting as the tireless, multi-purpose pioneers that prepare the way for humanity. Their inherent durability and energy efficiency are not just about surviving a 2-year mission on Mars. They are about operating for decades, perhaps even centuries, maintaining infrastructure and conducting science long after their original human designers are gone. Imagine a future lunar base, a bustling hub of human activity. Before the first crew ever arrived, a swarm of these adaptable machines would have already been there for years, having been delivered by an unmanned cargo lander. They would have spent that time methodically preparing the site, using their legs to carefully level the ground for landing pads, assembling modular habitat units with the dexterity of their limbs, and even mining the local regolith for water ice, a critical resource for life support and rocket fuel. These wouldn't be single-task robots. The same rover that uses a gripping foot to place a solar panel one day could use a different tool attachment to inspect a plumbing line for leaks the next, or venture out onto the hazardous lunar surface to repair a communications antenna during a brutal 2-week-long night, all without ever requiring a human to don a risky spacesuit. This capability for long-term, autonomous operation becomes even more critical as we look toward the most ambitious goal of all, interstellar travel. The vast, unimaginable distances between stars present a challenge that our current, fragile technology could never overcome. A generational ship, or even a sophisticated probe sent to a nearby star system like Proxima Centauri, would need to survive for hundreds or thousands of years in the void, with absolutely no possibility of repair or intervention from Earth. The robots on board, tasked with maintaining the ship's systems or exploring a new planet upon arrival, would need to be the most resilient machines ever conceived. This is where the lessons from insects are not just helpful but absolutely essential. An interstellar probe would need to be the ultimate embodiment of fault tolerance and adaptability. Its systems would have to be massively redundant, capable of losing multiple limbs or sensors, and seamlessly reconfiguring itself to continue its mission. It would need to operate on minuscule amounts of power, perhaps harvested from faint starlight over millennia, using the hyper-efficient movement strategies of a desert beetle that survives on scarce resources. Most importantly, it would need a profound level of intelligence and autonomy to handle any scenario it encounters in a completely alien environment, millions of miles from any human guidance. By embracing the evolutionary wisdom encoded in insects, we are not just designing better rovers, we are learning how to build machines that can become permanent inhabitants of the cosmos, enduring where fragile, short-lived technology would inevitably fail. This profound shift in thinking from temporary visitation to permanent settlement is how we truly build a foundation for humanity's future among the stars. These biomimetic robots are the unsung heroes of that foundation, the indispensable backbone of off-world civilization. They will be the constant gardeners in orbital habitats, the miners on asteroids rich with precious metals, and the sentinels standing watch over outposts on distant, icy moons. They allow us to extend our reach and our presence without constantly exposing human lives to extreme danger, creating a buffer of robotic resilience that makes human expansion not just possible but sustainable. This is the ultimate promise of looking to nature for inspiration. It teaches us how to build systems that are not separate from the universe, but are intricately and intelligently designed to thrive within it. By learning from the masters of adaptation who have conquered every environment on Earth, we are finally learning how to do the same elsewhere, ensuring that our journey into the cosmos is not a fleeting visit, but the beginning of a lasting legacy. From the fundamental constraints of wheeled systems on alien soil to the sheer evolutionary genius of six-legged locomotion, our journey has revealed a transformative shift in how we approach exploration. We've seen how the humble wheel, so effective here on Earth, can become a critical liability in the fine sands and jagged rocks of Mars, tragically cutting short missions like that of the Spirit rover. This vulnerability pushed us to look beyond our own inventions, to turn to the natural world's most seasoned explorers for answers. Insects, with over 400 million years of field testing across every environment our planet has to offer, provided the ultimate blueprint. Their multi-legged design isn't just about walking, it's a masterclass in dynamic stability, energy-efficient movement, and unparalleled obstacle negotiation. By studying the ant's strength, the cockroach's resilient speed, and the beetle's versatile grip, we are learning to build machines that don't just roll across the surface of other worlds, but truly interact with them, step by deliberate step. This biomimetic approach unlocks a future of exploration we could previously only dream of. It promises rovers that won't get stuck, that can climb crater walls to read the layered history of Mars, descend into the caves that may shelter signs of life, and anchor themselves to the surface of asteroids with negligible gravity. These machines will be more than just mobile platforms. Their limbs will double as manipulators, their feet will be sensitive sensors, and their artificial intelligence will grant them the autonomy to make real-time decisions, transforming them from remote-controlled tools into intelligent field partners. This isn't merely an incremental upgrade, it's a complete paradigm shift. It's about building resilience through redundancy, ensuring that a damaged leg doesn't end a mission, and maximizing our scientific return by finally granting access to the most geologically rich and tantalizing landscapes that have, until now, remained frustratingly out of reach. As we look to the horizons of tomorrow, from the icy fractures of Europa to the deep canyons of Mars, the principles of biomimicry will undoubtedly be our guiding light. This is more than just a technical evolution, it's a philosophical one. It represents a deeper wisdom, an understanding that the solutions to our most profound challenges have often been invented, tested, and perfected by the natural world long before we ever thought to ask the question. By blending the boundaries between biology and engineering, we are not just creating better robots, we are learning to build a sustainable and enduring presence in the cosmos, one resilient, insect-inspired step at a time. Thank you for joining us on this fascinating expedition into the future of discovery. If you enjoyed this journey, please subscribe for more content that explores the frontiers of science and technology, and let us know your thoughts in the